Right. Hey guys, welcome back to Teach Tigers. This is Venkat Muriki again, and as I discussed in the last session, the purpose of this kind of classes is to just bring some kind of awareness, confidence among the children who are preparing for inorganic chemistry and who always think that, or rather who are made to think that inorganic chemistry should be memorized, it should be mugged up, and therefore children start hating inorganic chemistry. So guys, let us be a little more practical. There is nothing like to hate inorganic chemistry because we are not going to have a lifelong companion of inorganic chemistry. Right? You are getting into competitive examinations. Obviously, whether you like or not, you got to like it. Implies, if it is boring, if it is not interesting, if it has been memorized to others, it shouldn't be to us. We need to work out a better solution, better mode, better method to really understand and have an edge over others in inorganic chemistry. Therefore, here the team Teach Tigers is now going to give a series of inorganic chemistry lectures on concepts, reactions, and definitely we are sure that we are going to make a small change in your perspective regarding inorganic chemistry. Let's start again. Guys, let's start this with an example. Now let me think as a student. If these 5 questions are given to you, what is the information you can compile about this? So let me imagine myself as you and let us discuss. The first question here, first reaction is ammonium chloride. So ammonium chloride you have here, ammonium sulfate you have here. And on heating, definitely which is an endo process, endothermic, you're getting ammonia is released along with HCl. And obviously, maybe this is your heat, so therefore assuming that this is above the boiling point, HCl also is vapor, and this is ammonia and of course sulfuric acid. Now there is something common in first 2 reactions as a student. As it is, ammonium chloride on heating is giving rise to liberating ammonia and HCl. In fact, these two are the acid and base which were giving rise to ammonium chloride on neutralization. Or I should say, ammonium chloride on heating is giving back to the acid and base from which it is formed. Same thing is true in second case also. Ammonium sulfate is giving back to its acid and base from which it is formed. However, if you look at the 3rd to 5th reactions, you can find small difference. Ammonium nitrate, this is ammonium nitrite. Ammonium nitrite, corrected. So ammonium nitrite is giving rise to nitrogen gas and water. Unlike the first 2 reactions. So usually ammonium nitrite on heating is not giving rise to ammonia or something called as nitrous acid. In fact, different products. Same thing is to ammonium nitrate. It is not giving rise to ammonia or nitric acid. In fact, it is giving rise to nitrous oxide. And very important one, ammonium dichromate is again not giving rise to ammonia or any other acid of dichromate. No. Dichromic acid is not formed. So, at first glance, you can find this difference. The first 2 reactions are giving rise to their acids and bases from which they are formed, whereas 3rd to 5th, they are not giving rise to acids and bases from which they are formed. In fact, the first 2 I can now say it is a simply non-redox reaction. Non-redox reaction. However, you can see 3rd to 5th, these are redox reactions. All this information I am compiling as a child, as a student who is now in 11th or 12th with basic knowledge of chemistry. That's it, guys. So, redox reactions, non-redox reactions. That's it. So, why is this happening? Why is this happening? If you look at this, again one more difference is chloride and sulfate. These are neither oxidizing nor reducing anions. However, nitrite, nitrate and dichromate. I'll write here nitrite, nitrate and dichromate. These are definitely oxidizing anions. Of course, in fact, nitrite is both oxidizing and reducing in fact. So this is the information I am compiling. Now, in the first two cases, though ammonia is -3 state, it has some reducing nature. However, chloride and sulfate, these are not oxidizing anions. Therefore, usually on heating, what happens is usually two kind of things will happen on heating. A redox reaction will be accelerated, its rate, speed, right? And also a reverse of nucleation reaction also will be accelerated. It moves spontaneously in the forward direction. Why? Look at this. First two. This is a reverse of nucleation reaction. If I say reverse of nucleation reaction, I'll take a blank here. Now look at this. Reverse of nucleation reaction. What is this? If I'm taking here simply NaOH with sulfuric acid, assuming it and definitely is a redox reaction, and as you know, it is sodium sulfate and water, right? And delta H in this case has to be less than 0, that is exothermic. This is what you learned in your school, you know. Nucleation reactions are exothermic, of course, is an equilibrium reaction, but it tends to move in the forward direction. So, if you apply Le-Chatelier principle, what is supposed to be here? So, this is forward is definitely exo and backward has to be endothermic reaction. Now, connect this to the previous case. Ammonium chloride. Here, ammonia with HCl should give you ammonium chloride, that we know, an equilibrium reaction, and delta H has to be less than 0, exothermic. Now, in the previous case, what are we doing? We are heating it and it is reverse. So, I am now heating this. If forward is exothermic reaction, as we know, backward is definitely endothermic reaction. Therefore, on heating, ammonium chloride has to decompose, no doubt. And secondly, it is decomposing and giving rise to backward reaction, and chloride being a non-oxidizing anion. Therefore, as I told you just some time back, on heating usually redox reactions will get accelerated. On heating, so therefore here chloride being non-oxidizing anion, it cannot oxidize ammonium. It cannot oxidize ammonium, and secondly, since on heating it, the backward reaction is favored. The backward reaction is favored, so obviously the backward reaction has to be decomposition of ammonia chloride to ammonia and HCl, because though ammonium is a reducing cation, chloride is not oxidizing anion. That's the point. And on same lines, you get this ammonium nitrite, ammonium nitrate and ammonium dichromate. Here, let's take an example of dichromate. Dichromate here, as you know, we are taking ammonium dichromate. Cr2O7. This upon heating was giving rise to nitrogen gas and chromic anhydride plus water. This is orange, yellow, solid. And the point of interest in this case is, whenever you are preparing for inorganic chemistry, you got to know the colors of the compounds, precipitates, gases, important characteristics of very important compounds. It is always you have to know. Therefore, I have here nitrogen is colorless gas, we know, and however this is anhydride, orange. Now, why is this happening here? Why is so? I can say now say simply here these three are simply redox salts. However, the first two are non-redox salts. So, how do you identify that? So, obviously, the salt should have one component as oxidizing anion and other component as reducing. In this case, ammonium is reducing anion and dichromate is oxidizing anion. And moreover, you are heating it. As I told you, on heating, definitely it will accelerates redox reactions. Usually redox reactions take place at high temperatures. So dichromate being oxidizing, ammonium being reducing, definitely you are providing a perfect experimental condition for redox reaction to take place. And now how do you guess this product of nitrogen and Cr2O3? Simple here. Now dichromate already we know, Cr2O7, dichromate anion, it is in +6 state. Being oxidizing agent, always it is the case, it accepts 6 moles of electrons. 1 mole of dichromate always accepts 6 moles of electrons. Therefore, here we have 2 chromium in +6 state. Each of that has to accept 3 electrons. Therefore, you end up with Cr+3. The product of dichromate has to be Cr+3. And however, what is the source of this 6 moles of electrons? Definitely ammonium. And ammonium being a reducing anion, it has to lose electrons to dichromate. So how many it has to lose? Definitely in a redox reaction, electrons lost should be equal to electrons gained. If dichromate is gaining 6 electrons and ammonium has to lose 6 electrons, implies there are 2 nitrogens here. Each has to lose 3 electrons. Implies this is already in -3 state. So each nitrogen atom losing 3 electrons implies nitrogen -3 should end up with nitrogen 0. And that to 2 nitrogens. So this has to be N2 gas. Therefore you have N2 gas. And chromium +3, and therefore we have oxide, we are heating it. So this chromium +3 has to combine with oxygen. And therefore it has to be Cr2O3, wherein chromium is in +3 state, same thing. So guys, this is how we do it. And of course, water, you have hydrogen, oxygen, definitely the temperature is above 100 Celsius, therefore the water will be in the vapor phase, that is understood. And this is that important. So dichromate salts, nitrogen compounds are definitely very important. So if you look at previous IIT, previous NEET and previous most of the entrance examination, number of times this compound was given, including last year. Ammonium dichromate, I think in the mains it was given, 2020 mains. Ammonium dichromate giving rise to N2 plus chromic anhydride and water. So the key point here is, how do you identify the salt is redox salt or non-redox salt? So it all depends on what are the anions and cations. So we have to know which anions can be oxidizing, which anions can be reducing or whatever. The anions and cations, you should know how to identify them as oxidizing or reducing. That is the basic concept. That's it. And moreover, I'll give some logic for this. Usually, again, this question was asked number of times, and usually children get confused. Children get confused about when to these two. So if I take your ammonium nitrite and ammonium nitrite you have and ammonium nitrate you have. So this again, both are definitely redox salts. Now how do you guess the product here? Simple logic. Look at the oxidation number of this. Here it is -3 and here it is +3. -3 and +5. The logic goes this way. The average of these two will be the product of this. Oxidation number average. What is the average of -3 + 3 is 0. Therefore, it is N2. Definitely you have oxygen hydrogen. Water is more likely. Here -3 + 5. Average is +1. So, what is the oxide of nitrogen +1? It is N2O. N2O plus water. This way you can overcome the confusion between the products of ammonium nitrate and nitrite. Right. And why is this N2 only? Why not something else? Why is N2O? Why not something else? That we can't answer unless we have some data from thermodynamics. Alright. So therefore guys, here if an option is given, which of the following are redox and non-redox salts? Definitely these three are redox salts and these two are non-redox salts. That's it. So this is how the concept is involved in this case. And why do you think these three questions are always occurring in the entrance examination? Why are they asking? Because the paper setter have to test you whether are you aware this is an oxidizing and reducing or non-redox. This is the basic concept which is being tested. That's it. All this we have done yesterday. We'll discuss let's discuss this kind of reaction wherein this is one more. A lot of concept is involved in this. So here now again as usual, the question asked in many of the entrance examination including IIT was this. Boron is coming from third group element. This is BF3. So usually the comparison is between BF3 versus BCl3. Boron trichloride or sometimes BBr3 also from 13th group elements. Here if you see the textbook, BCl3 undergoes hydrolysis and giving rise to boric acid and of course HCl. This is 3 moles, let's balance it. 3,6 means this. This is a very common reaction given your textbooks, asked in your board exams, asked in your most of the entrance examination. Here the statement says that BCl3 undergoes complete hydrolysis. He uses the word complete hydrolysis. The meaning of this is BCl3 undergoes complete hydrolysis and means it is giving rise to only boric acid. Only boric acid. Means the meaning of complete means it is giving rise to only one compound of boron, that is boric acid. Then why is that? BF3 on hydrolysis is giving rise to two compounds of boron, boric acid and BF4 minus. Boron tetrafluoride, BF4 minus. Why is that? Implies this boron is getting distributed here. It is not completely converted to boric acid or completely converted to BF4 minus. It is getting distributed. So his question was, why is that? Why is that BF3 undergoes incomplete hydrolysis like this? Because usually complete hydrolysis means boric acid. But here you can see, out of 4 moles of BF3 used, 1 mole only of that is giving rise to boric acid and other 3 moles is BF4 minus. So this made to tell us that BF3 undergoes incomplete hydrolysis. It is also having some side product called BF4 minus. So why is that? That is a question. So number of time question was asked. BF3 undergoes hydrolysis, complete hydrolysis to give the following compounds A, B, C, D. In that A, you can see only boric acid. In that B, you can see only BF4 minus. In the C, you can see both. In the fourth option, none of something else. So, what you got to know is, the key thing is, this is something different. Why is that it is undergoing incomplete? Why is that it is spreading out into 2 different products? So, we need to give some kind of conceptual explanation to make this reaction interesting. Let us try this. Yeah. Now, what is that we know about this? Here, let us now understand the reaction. Let us understand the reaction, what is happening here. BF3 with 12 waters is giving rise to boric acid and HF. The reaction is not stopping here. It is not stopping here. Not stopping. In the second reaction, you can see this HF is further, the products are again reacting to give rise to BF4 minus and all this stuff. What made the 2 products of first step reacting? And because of that, the resultant product is not exclusively boric acid, also BF4 minus. So some concept we can try here from chemistry. Yeah, this is understood. BF3 with water. So maybe some logic. It is not the mechanism, but just to make it more interesting, we are doing it. So BF3 on hydrolysis, we have learned this earlier also. Boron is electron deficient, it has vacant orbital, and therefore the lone pair will coordinate with this boron. And ultimately, this is one thing. And therefore, this BF and OH2, this is what we learned. F, 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 and this is minus. And subsequently, the proton is lost and one fluoride is lost. This is giving rise to BOH. Subsequently, this is a case. A simple mechanism. It is not a proven or we don't have experimental evidences. Only to make things simpler, we are giving it. That's it. So, now this fluoride and H plus is where HF is there. Now, first step can be explained like that. So, every BF3 is giving rise to boric acid and this. So, therefore, we have 12 fluorines, therefore 12 fluorides. That is very easy to understand. Now, what made the second reaction to happen? What made second reaction to happen? Here, probably HF. What is that you know about HF? If you remember in hydrogen halides, HF, HCl, HBr and HI. Try to recollect. Acidic strength is increasing. Increases means HI is strong acid and HF is weak acid. And you learned one more point, A conjugate of weak acid always results in a strong base. Means if HF is a weak acid, its conjugate is a strong base. A basic concept which you learned from ionic equilibrium in your 11th standard. So fluoride is a strong base. If fluoride is strong base from the equilibrium, what is the case now? There is a possibility here, this fluoride can attack the boric acid again with a vacant orbital and coordinate like this. So this way subsequently all the three are giving rise to BF3, but it doesn't sound sense. It doesn't sound sense if the reaction stops here because it is the same reactant. However, now you have excess fluoride in the system and coordination number of boron is always 4. You should know that. And BF4, so this BF3 which is formed will again react with one more fluoride and giving rise to BF4 minus. Means boron has achieved its maximum coordination number which is 4. Therefore, this compound is more stable, thermodynamically more stable than BF3. BF3 always is, it is unstable, it is electron deficient. It always looks to react with any species which is electron donating. And here you have fluoride electron donating, therefore BF4 minus is formed. So what is the point in this case now? Here, out of boric acids and 12 fluorides here. Now how many we need here now? How many we need? Each boric acid, here there are 12 fluorides and each boron should convert to BF4. So each boron to convert to BF4 means each boron needs 4 fluorides. So 4 fluorides. So therefore, if 4 fluorides are there, definitely what is the possibility now? What is the possibility? Out of this 4 boric acid here, means you cannot expect all 4 moles of boric acid to convert to BF4 minus. Because if all 4 boric acid has to convert to 4 BF4 minus, it needs 4 into 4, 16 fluorides which are not there, it is only 12. Therefore, a partial reaction happens. 12 fluorides will react with 3 boric acids converting to BF4 minus, a more stable compound, and 1 mole of boric acid will be left out like this. So this conjugate base, fluoride being the strong conjugate base, that is more reactive in the equilibrium, that is tending to react with boric acid and convert into BF4 minus, and this is not possible in case of, if I replace this with BCl3, here you have HCl and definitely Cl minus is not here. HCl itself is strong acid. So Cl minus is a weak conjugate base. So therefore, we cannot expect this reaction to happen with HCl versus boric acid. This doesn't happen. And there is nothing like, more stable of BCl4 minus is definitely not as stable as BF4 minus. Because fluorine-boron coordination number is completed and BF bond is definitely more stronger than BCl bond. Therefore, you cannot expect BCl4 minus to be formed for 2 reasons. This is not stable as this. At the same time, you can't expect Cl minus. Cl minus is a weak conjugate base. The second step may not happen. So probably this may be one of the possibilities why, the boron in BF3 is getting distributed in 2 cases. Right? And so this concept is there. That is the reason we have so much of, chemistry in this, and therefore it is interesting for the paper setter. That's it. So remember guys, paper setter will never test your memory skills, or he will never pick up a question or concept from some corner which is never important. No, it is only important things. He is going to test your basic concepts. That's it. Alright. Yeah guys, the final reaction for this session. What is this compound? At first instance, most of you may not be able to recognize this compound. This is nothing but here borax, Na2B4O7.10H2O. This is borax. So usually, now same thing if I will compare this with CaSO4.2H2O. We say these are the water of crystallizations. Here, if same thing is asked in borax, what is the water of crystallization in decahydrate? Definitely 10 is water of crystallization is wrong. This is wrong. 10 are not water of crystallization. I mean to say 10 moles of water are not hooked up with Na2B4O7. No. It is different. Now let's see. So this is how you see that Na2B4O7.10H2O. Structures are definitely one of the most important areas where questions are likely. So very important compound structures you got to know by practice all the time. Now how do you look at this? Na2B4O7.10H2O. This is boron. All the 4 boron atoms are tetrahedrally oriented with a bridged oxygen like this. And one more oxygen should be something like this. And here on every boron you have one OH group. OH group. Look at this. This part is more or less triangular planar. So this is TP. However, this is tetrahedral. Tetrahedral oriented. Now look at the charges. Boron coordination number is 4, therefore it has minus charge, minus 1 charge, and this is as usual. Since minus 1, minus charge, you have cation associated with this, Na plus, and you have Na plus. Now count it. All you have is now Na2. Open this. Borons are how many we have? 4 borons. Let's say B4. How many are linked oxygens? 1, 2, 3, 4, 5. B4O5. Then what we have? OH groups we have on each boron. So therefore OH4. So Na2 Na2B5OH4, and then you have the so-called 8 waters, because out of 10 waters 2 moles of water are part of this. You can see now Na2B4O5 and OH4 means obviously 2 moles of water are involved here, and this is 8 waters. So on heating, obviously 8 moles of water at normal temperature will be coming out. So therefore we'll say water of crystallization is 8 and not 10. Careful. Alright, this is one part. Now if you see what is the reaction here, reaction is this borax is now reacting with some HCl and all this stuff. So how do we explain that? Yeah. Done. So it is reacting with HCl. Yeah, what is the possibility now? Now first of all, before reacting with HCl, this is water obviously. Now What is the reaction? Check it out once. You have HCl reacting with giving rise to sodium chloride, boric acid and waters. Yeah. Now, the point of interest in this case is, in the first step, it undergoes hydrolysis. Means these bonds are definitely, they're like strained bonds, like cage-like structure, strained. So given a chance, they always try to break it. So here you can see that how do you break it? Just break this. All BOB bonds are highly under strain. So given a chance, they will break it. So first these bonds are going to break on hydrolysis. On the side of, I'll change the color. On the side of hydrogen, you have H plus, other is OH minus. So same thing, H, OH. Yes, H, OH. H, OH. H, OH. So how many waters we have used? 5 waters. So 5 waters first undergoes hydrolysis, because boric acid, as you can see, this is completely, aqueous medium. Therefore, first boric acid undergoes, borax undergoes hydrolysis. And what is that giving rise to now? This part is what? This part. Here I have, this part will give you 2 moles of boric acid plus 2 moles of BOH4. The first step is hydrolysis, wherein you are getting 2 moles of boric acid and 2 moles of BOH4 minus. Now the question is, if you look at the reaction, it is reacting with HCl, an acid. So where is that now? Now where is this? So here, with which HCl should react? This is definitely an acid, but this BOH has OH minus, which can act as a base. Therefore, the HCl which you are taking, H plus and Cl minus, H plus will abstract OH minus from that. Because you can't expect an acid to react with one more acid here. Both are, and therefore, and moreover, this is acting as a base. This is BOH4 minus is a base, definitely base. So this is base, this is an acid. Why is this base? If you look at the structure, BOH, OH, OH, OH. All the bonds are saturated. There is no need for boron to accept alene electrons. In fact, the possibility it can lose this OH minus. Therefore, you have a base. So therefore, this H plus will abstract. I have 2 moles of BOH4 minus. Therefore, 2 H plus will abstract. 1 each results in 2 boric acids. Therefore, guys, 2 boric acids here, 2 boric acids here. Ultimately, all you're getting is 4 boric acids. And what about NaCl? Where is NaCl? Chloride is here and sodium is here. We have 2 sodiums and obviously 2 chlorides. That should give you 2 NaCl. 2 NaCl. That's it. Alright. And balancing is what now? What is balancing here? You can see the balancing part. 5 waters are coming out. Where are these 5 waters coming out? Here. 5 waters. Where are the 5 waters coming out? We have first used, in the first step we have used how many waters? In the first step, how many waters we have used? In the first step, we have used 5 waters, giving rise to boric acids and to this. And how many waters are formed further? You have 2 moles of waters are formed here. So what a net change here? So this 8 waters and giving rise to, finally again they are giving rise to 5 waters, means 3 are consumed. That's it. So therefore, NaCl, boric acid and water has to be explained this way, right? So this is how guys, more or less most of the reactions which has importance in one or the other area, and those reactions where a good amount of concept is involved, and definitely paper setter is interested to test those. So all you guys, what you need to do is apply some concept, make it interesting, because there is no way you can escape it. You can't blame inorganic, or you can't say that it's competition. If you are not getting into inorganic chemistry, your competitor is going to get into inorganic chemistry, and definitely he's going to score more, right? So this is how our series of lecture will continue, guys. And in the coming days also, we are going to start with the group 1 to group 7, 8, coordination chemistry, a lot of other chapters, physical chemistry we'll be doing in this series. Alright, thank you. Shalom.